We now move on to Mike DeFreitas' presentation, connection with the William Smith Medal. Mike, over to you.
Well, good afternoon, ladies and gentlemen. I called this a homage to William Smith because he at least succeeded in getting something completed. And it's in three parts, basically, which I'll tell you about something about London, something about clay slopes, which has an implication for insurers and local councils, and something about mineral boundaries, which has implications for the way in which we could actually begin to look at rocks and soils in the future. Starting off with London, if you look at London's rivers, you'll find that they are a bit strange. We are, after all, if you look at the maps, on a basin with floodplains covering clay, and on the clay there are sands and gravels. So you wouldn't expect, when you look at a map of London, this is a map showing a lot of the rivers which are now in culverts and streams. You don't actually see them on the surface. There's a tremendous linearity to these things, which is very strange. And not only that, in London, you find there are these odd features, very zones of gravel, which cause terrible problems with certain engineering. For example, if you're sending the London Underground through here with a clay tunnelling machine, the last thing you want to do is to bump into something like this, but unfortunately they do. So we've got strange rivers and we've got strange structures right under our very feet, not very far from where we are now. And here's an example on the sort of scale that I'm working on. We've just heard about volcanoes. Well, here we're much shallower, and these are the foundations of buildings, all planned on the basis that we're in one sort of material, and we find ourselves in something totally different. So here we've got London clay, and here we've got all manner of other disturbed materials. So these things cause real engineering problems, real delays, and that's where the money goes when things begin to not go according to plan. And here's a street map. You might just see the sort of scale. That's Finsbury Park. The street map giving you some size is a contour diagram of the sort of anomalies that you can find. So not so easy to locate under cities. Now, if you look at London, you'll find it has a very strange structure. And I remember in the 70s when this came out, Water Resources Board, 1972, somebody decided, in fact the Water Resources Board decided to plot the top of the chalk. They had gathered an awful lot of information now from wells, and the top of the chalk was a sort of a horizon you could identify fairly clearly from the stuff that was above it. And what came out was this extraordinary map that looks as if the top of the chalk is like sort of the top of the sea, up and down, up and down, up and down. Whereas you go and have a look at it, in the North and South Downs, it looks perfectly normal. So what was all this doing? And why were there outcrops of chalk up here? And why is it that were faults formed along here? So there's a whole thing here, very, very interesting plot, with no explanation really in it at all. And there were other strange things beginning to appear. An extension, this is Windsor, that's Heathrow. I wonder if we could just, can we lower the lights just a little? There's a lot of light down here, I don't know if we can. There's an extension, here's Heathrow, and here are the reservoirs around Heathrow. And what was being found up here, a place called Prospect Park, was clay for building. We were using this for roads. It's called a borrow pit. And the clay in the slopes of the borrow pits failed, and the failure turned out to be an old failure surface. And when the moisture content of that profile, this is depth and this is water content, was actually measured at a centimetre scale. So these are little samples taken, and you can only do this for students, you need slaves maybe to do this. On a centimetre, we find actually that the moisture content, as it got into the failure horizon, decreased and then back increased. Now that's quite contrary to what you might expect. You probably don't know a great deal about soil mechanics, but if you had a dense clay, a tight fabric, the clay minerals are all tight together. If you want to shear them, you have to dilate them. They all have to move, they have to open up. And so in fact, then the pores open up and water gets sucked into them. So actually the moisture content increases as failure occurs. Now here we've got a failure surface with the moisture content decreasing. And the only explanation for that is that that failure surface occurred whilst the sediment was basically undergoing its consolidation. So what are we doing with low angle shear surfaces going in at the time London clay was being deposited into London? What was going on? So we've got these very strange sorts of information in London itself. The anomalies, the strange rivers, and in fact horizontal shear surfaces that went in early on in the geological history. Well, if we go back, the answer to this is really, in my opinion, is in the rivers. If we go back to the rivers and we draw them out, and we draw out their intersection where they bend, you find you've got a sort of linear pattern. Now that's very, very strange, isn't it? What on earth are we doing with that? You take away all the background, and we're looking at something like this. It was like a typewriter board, up and down, up and down, up and down. And we went to see Thames Water about this, and confirmed that these blocks represented areas where there was definitely a difference in the elevation of the chalk. So whereas the Water Resources Board looked at the chalk as a continuum, we're now looking at the chalk as a discontinuum. In other words, it's broken up into blocks, and the blocks are separated by, well, what would separate blocks? It has to be faults or something like that. And the interesting thing about this is that when you go back to the rivers, and you look at the linear sections on the rivers, and you plot them out in a fractal way, that doesn't explain anything, it's just a description. But the interesting thing about it is they lie on a line which is the same sort of line you get if you go off and you measure faults. You go and measure the linear lengths of faults and their frequency, and you land up with plots looking very similar to this. So we had a real mishmash of information coming in about what was going on in London. And a few plotted also where the anomalies are. I don't know whether you can see this. I don't think there's anybody up there. If there's anybody up there, could you turn the lights down a bit? But there's no one up there. No. Well, anyway, look. Oh, there we are. Thank you so much. Well, you may see some red dots. These are places where these things called anomalies turned up, and engineers got into problems. And surprisingly, they start lying on these lines. So here now, you've got two totally different sets of data beginning to co-register. Now, this has to mean something. And we took those linear lines again and we put them onto this sort of information. Again, these are the lines you get from the river, and they now begin to line up with these sorts of domes which are occurring in the chalk. And again, if you take, this is from another totally different set of data. This is from the Water Resources Board, water levels in the chalk. Now you would expect London, having been over-pumped, to be one huge dartboard appearance, just a big cone of depression. But it's not like that for water. Actually, it's quite a square of depression rather than a cone of depression. And this square sits bounded by these lines which we see from the rivers. So how is it that rivers are actually reflecting what's going on at depth? I mean, the chalk is quite deep there. Well, the answer, in my opinion, came from the fact that we're getting influence from the Variscan front. If we put the Variscan front in, here's southern England, here's the Variscan front. Here we've got our alpine and present stress directions. And if you've done any sort of rock mechanics or any sort of structural geology, you know that if you take a flat surface and you shear it, that's fine. But if you don't take a flat surface, if you take a surface that's got a few bumps in it, then in order to make that work, you've got to displace it. I can see you. Can you see me through the gaps? In other words, you get gaps. Okay? You've got to displace these things, you get gaps in them. And that takes us through to the answer. It's pull-apart country. Underneath us feet, we've got pull-aparts. And it means that we've got places where we've got the dead, boring, layer cake geology, separated by steep surfaces when anything goes. Quite remarkable changes in geology can occur. And the people who bumped into this in a way, first of all, were Thames Water. This is up in Plaistow, northeast London. They had a tunnel that was going to go through, and fortunately for them, they just did one more borehole, and suddenly they realised they had a major problem. And this was what came out of that eventual study. Here we've got the chalk. Here's the material above the chalk, and look at these displacements. We're talking here of over 10 metres of displacement. with everything quiet and horizontal and London asleep above it. So that is the story that we've got going on in London. And what does that mean? It means that if we've got pull-apart basins and these sorts of local characters, we've got a bit of a problem with our data banks. Because one of the things that companies like to do is to keep their data. So, and one of the things that they would like to do is say, well, we've got data in relation to depth. Here's a geotechnical parameter, and there's depth. And nature isn't stupid. It provides us with a variation with depth, which is usually understandable. If then you have a displacement, so that in one place you're looking at a depth profile like this, and another place you're looking at a depth profile like this, same low area, so to speak, then quite clearly this is going to be further displaced. So if you start putting your data banks, site 1, into the same data bank as site 2, you land up with a bit of a spread. And if you look at some of our geotechnical data, in fact quite a lot of our geotechnical data that's in data banks, it looks like this. So we've got data banks that really need tidying up because they are very, very important indeed. And the other thing that's very interesting here is that if we look at the London Underground, having seen this now, if we look at the London Underground, that's the map we all know, but this is more like what it really is. We are actually looking at basically the nuts and bolts of a strain gauge if we wanted to monitor it. Because these things actually do have evidence on them that they are still active. Now, this work has been taken on by others from me, but if we were, and we don't at the moment, but if we had the opportunity to strain gauge a large part of the London Underground, we would have a wonderful picture of a chunk of crust, the like of which, and its movements, the like of which we don't have at all anywhere else in the world, and it would be very instructive indeed. Well, that's London. Moving on to a different sort of movement altogether was going down to the Isle of Wight, down to Ventnor, which is down here. Now, Ventnor is, quite like quite a few of the places on the south coast, is plagued by landslides. You see it everywhere, cracked walls, bent roofs, and builders. It's a good place if you want to set up a building firm, go pick somewhere where they got landslides, because you're never out of work. There's a lot of fresh paint down in Ventnor. And the question is, how do you actually cope with the infrastructure and for the insurance in places like this? These slides start off in this sort of fashion, but if you go and you see this as their topography, and it's quite clear how they initiate it, and there's very good reasons for that. But if you go back now and look at what they're doing at the moment, and instruments have been put into these landslides of Ventnor, you get a very, very different picture indeed. Those pictures, you can see from there, there is a sense of rotation. Things have gone like that. So you'd expect those sorts of movements to occur. Somebody's got a house here, opposite, somebody's got a house here. Suddenly there's a crack in their swimming pool, the swimming pool disappears, you know, bottom of the garden goes down. You know, those are the sorts of things you'd expect to be going on. But when you actually monitor what has been going on, you find a different sort of picture altogether. These are inclinometer profiles. Those are tubes that you put into the ground and you watch how the tubes move with time. So here we've got deformation, here we've got depth, and these tubes, these profiles are different times. This is one location. This is how the ground moved 110 meters down in September. That was the profile in September 2002, September 2003, August 2004. And I showed this to some of my colleagues in hydraulics. I said, if you saw something like that, how would you describe it? He said, oh, well, without a shadow of doubt, before the coffee cup had reached the lip, stratified viscous laminar flow. Boom, just like that. Well, now you don't find that in the solution techniques for looking at slopes. But it provides us with a very interesting way of looking at this sort of ground for these sorts of communities. Because basically what we've got is almost a steady flow. And now that's a perfectly amenable thing. You can handle that sort of thing with insurance. You can handle that sort of thing with utilities. It's the unsteady flow, the suddenly things going, that cause the problems. So there's an area where it seemed to me that there was a lot more that could be done. And finally, I just want to say something about an intriguing area of research, certainly for myself and some of the colleagues I was with, and that is how do we describe our material. Now, you'd think we'd know, actually, how to describe our material, but the fact of the matter is it is very, very difficult indeed. We either describe it with words, which never captures it properly, or we describe it with numbers, which still leaves us with a gap, or we describe it with pictures. But how do you sort of bolt all this together? It's very, very difficult. And that was brought home to me when Salisbury Cathedral was undergoing some period of renovation, and the original stone, the Tisbury member, which was used originally, which looks like this under the microscope, had to be replaced. What do we replace it with? There was nothing around in Tisbury for the Tisbury stone anymore, and the nearest they found was the Chilmark stone. That was replaced. So the Tisbury stone was used when they built the cathedral. It was replaced by the Chilmark stone in the 19th century. The Chilmark stone didn't weather anywhere near as well as the Tisbury. So what was the difference? Could we have another one, something different from the Chilmark stone? And by the way, what sort of tests do we do to find something that is better? And I was in the architect's office. There was, I think, 2 shelf meters of test results, and nobody had the first idea of actually how to use any of these results. Just about every sort of test under the sun was done on these things to try to say, well, obviously that one's better than that one. So we tried something quite different, actually, and we took a sample, dried it out very carefully, not with heat, but we dried it out and just exposed it to vapor, water vapor, and watched how the sample actually took up water. So this was, you were doing nothing to the sample at all, you were just exposing it to water and watching how it took up water. And these things are repeatable, they take a long time. I mean, this is quite a long, you divide that by 24, you find there's quite a few days in here. But you see outcomes of fingerprint. And this is the fingerprint stuff. The sample's telling you what it wants to say, it's telling you how it is. And it actually gives us a marvellous way of describing one sample from another. It would be a very great help to us indeed if actually in rock mechanics people not only describe their rock in the usual petrological way, but they gave us a fingerprint like this, because you could then say, actually, my sample looked like that, or my sample, which had the same name, totally different from that. So this is a way in which we can actually do things which we can't do at the moment, and it costs next to nothing, actually. It just takes a bit of time. Well, that took us on to this whole business of what's going on. Why do you get this? It's all happening on the surface. It's all happening on the surfaces of grains. I did an honours min and pet, 3 glorious years squinting down microscopes, and years after that as well. And I went back to my books to find out what I had written in the books about boundary layers in minerals. I had precious little indeed, because of course they're very difficult to see. You can't discriminate them under a petrological microscope. You look at them under electron microscope, you don't really see them in these sorts of forms, etc. So here's a piece of work that was done by the father of a colleague who's here today, Christine, which shows us a bit more about how boundaries might operate. Here's a stream in Germany where ordinary alluvium, recent alluvium, sands made out essentially of quartz, there's feldspar, there's mica, etc. The usual suite of resistate silicates. Samples were taken and put into 2 solutions. Well, one actually, well, what have we got? Here's a graph of silica concentration, and here's time. And this is water saturated with silica at a concentration equal to quartz solubility. And this is down here the results of what happens when you take this sort of material and you put it into distilled water, and the concentration of silica quietly heads off, clearly heading towards this equilibrium. And up here is water supersaturated with silica, and you put these particles in, and here it is chuntering down towards this boundary. In other words, regardless of whether this was mica, feldspar, quartz, it all seemed to be behaving like silica. It was all wearing a silica coat. And what does that begin to tell you about the boundaries of these minerals? Well, it begins to open your eyes and tell you an awful lot. And when we start looking at weathering profiles like this, and where strength is, and where deformation and stiffness is, and where our sonic velocities are, and a whole mass of other properties, it begins to point towards the fact that we may well need to look at our boundaries. And here's a little diagram from the same work that I mentioned from my colleague Christine Butenith, who's written a book on strength and weathering of rock as a boundary layer science, actually. It shows us where these sorts of things could come from. And the point is, if we have gels, and these are silica gels, they will have a very small porosity, Big one. That's all right. These things happen. They will have a porosity, but it will be made of very, very small pores, micro, and the suction that you can get inside those is immense. So this begins to explain the response of rocks to water. It begins, in my opinion, to explain why we have things called effective stress as well. I think this is a part of the story that was really only just started, but I'm afraid I've got to end. So thank you very much indeed.
Thank you. Mike, you've run off. I don't know if there are any questions that you might really like to answer. I don't know, you're safe running off perhaps.
One quick one. Have you looked at the distribution of sinkholes in the chalk mine to see whether there's any relationship between them?
No, I have, but I know somebody who could.
Thank you very much for that quick answer. There's one more over here.
Why are they strike-slip faults, in your opinion, underneath London as opposed to any other process?
It just seemed to explain it most fully. Subsequent to that, the engineering community has now, alerted to this, has now been observing and interpreting what would otherwise be described as anomalies by engineering sites. So these are in sort of Oxford Street, quite local stuff. And a lot more work has come out now where these things have been properly mapped, which seems to fit into that understanding. So, I don't know, that's the sort. It seems a simple observation, and the observations so far seem to fit into it quite well. The interesting thing is, somebody's turned up with one site where we've got inverted structures, and it looks like as if we've got cauliflower. They hit compression. It's dramatic. You find the inverse structure.